All right, looks like we're live. Perfect. All right, so welcome back everybody to another stream on building a balancing robot with the Pico W. So to recap from last time, we re-implemented the I2C driver that came with I2C devlib to use interrupt-driven mode and DMA to read data from the MPU to fix the freezing problem. And since we didn't have to worry about the freezing, we moved on to building the logic that controls the motors. And then we implemented a very simple PID controller in our main task that essentially tries to balance the robot vertically. And that let the robot, that gave us a very rudimentary balancing. We spent about the last 30 minutes doing some tuning, and it can stand up on its own, but the robot is horribly jittery. It's very jittery, and also doesn't really stay in one spot. So still needs more tuning, but currently what we were doing in the last video was the only way to tune it was to bring it back onto my desk, plug it in, update, tweak the constant, and upload the program again, rather than being able to just change the constants on the fly. So today what the goal is to build a visualization tool to build a visualization tool so we can see the data coming in from the IMU, see the current response of the PID controller, and also give us a ability to change the PID constants on the fly. And just to give an idea of where the robot currently is in terms of performance, I will turn it back on. So let me grab my phone here, switch over to the desk cam. All right, let me power up the robot. I just believe that would mean I put in the battery like this. I'll restart the microcontroller, and the wheels should come back on here at some point. Alrighty, and so if we pick the robot up, it's not very happy with me, but if we put it vertically, it more or less balances. But it jitters around pretty bad. Like, you can try to hold it in one spot, and it'll kind of stay there, but the jitters will build up, especially if you tap it. You can see how jittery the robot is. Stop. You can see how bad it jitters. So, goal is to fix that. And the first thing that might actually be wrong with it is that... Oops. The first thing that actually might be wrong is that... Let me just turn off these motors so you can actually hear me. Alright. That was the logic, not... Oops. Oh well. I guess we'll power down the other side too. Alright. So, the only thing... So one of the things that actually could be wrong is that this IMU is actually mounted on double-sided tape. So, it's not secure, really. It can move around quite a bit. And if that's wobbling, well, it will think the rest of the robot's wobbling. So, despite what you might think, where it might seem intuitive that you should isolation mount your IMU, the problem is if you do isolation mount your IMU, you can't actually detect how much you're jittering, so you don't actually know what the current robot state is. So, we actually should first start off with, before we get too much at anything, is design a solid mount for this IMU. And so to start off this evening, what we're going to do is just quickly 3D model a new mount for this thing that has some inserts to basically let me put some threaded inserts in to securely mount the IMU, and we'll actually just super glue that IMU mount to the robot, but we'll use threaded inserts so we can recover the MPU if need be. So, let me switch back to the desktop cam. Put my phone to sleep. Alright. So, let's open up a CAD tool, such as FreeCAD. And what we'll first start with is opening up the 3D model I made of this balancer in the past, which should be balancer.freecad. We'll let it recompute. And this is the 3D model that I made of the balancer a long time ago, mainly for printing it out. And the IMU is currently mounted in the center here. So we shall start with, all right, that's the stand that I printed. So let's see. I think we can actually start off with battery holder, actually. You know, I probably, in another document, have the bits and pieces, because before, a long time ago I didn't realize I could actually have multiple good parts inside of, here we go, IMU spacer. This is actually what the little piece of IMU spacer looks like, and we'll just model this again in the document for the balancing robot, rather than this crap. What is this? 38.7 mil. Is that actually how long this thing is? Parameters. Chassis depth. 40 mil. Okay, so we shall look at balancer 1. All right. And you know what? Let me actually take a set of calipers and measure how thick the robot is, just to see how close the print I made a long time ago actually comes to the real thickness of the robot. And yeah, so even though we defined it in the 3D model as 40 millimeters thick, the Ender 3 that I printed this on years ago made it 38.7 millimeters thick. So it got kind of close, but not quite. So and the reason that's important is that I now have a Bamboo P1S and it's a lot more accurate. So we'll make a new mount, and we'll design it to be as wide as it's actually supposed to be. And all right, so let's start with making a new part. So we'll just turn off the visualization for this. Why can I still see that one motor? You know what? It's probably... I see. It's the mirror. Bracket L mirror. All right. That's funny. Okay, sorry. All right, so we're going to create a new part. We'll go to the part design toolbox. Let me maximize this just so y'all can see this easier. We're going to start here. We're going to create a new part, and that is going to be called the IMU mount. Then I'm going to create a body, which we'll just call, we'll just call IMU mount body, rename, that's F2. Body, I'm going to start with a sketch, and the sketch is just going to be, just to start off with, we're going to do a centered rectangle. I'm going to do that just to make it easy. We're going to constrain how long that is. It's going to be parameters dot chassis depth. All right, and then the width is going to be, I'm just gonna set that as 20 millimeters just until we figure out how wide we actually need it to be. I'll go back, we'll go back to our parameters. We'll then say IMU width. We'll change the alias of this to IMU width. Then we're going to define this as we're going to take our set of calipers. We're going to take an IMU MPU 6050, and we're going to take the width. Let me just make sure that's zeroed. We're going to take the width. That's 20.25 millimeters in width, so that's good. Actually, what we do want to do is make this a bit thicker than it really is, because we're going to be mounting the screw holes essentially for this MPU, if you can see it. These are very close to the sides of the PCB, and the threaded inserts are going to be far in excess of the diameter. So we'll just need to make sure that we make it wide, give it enough clearance. So we're just going to say we're going to make the mount 20... We'll just say 22.5 millimeters for now. That'll give us a little bit of margin on each side, hopefully. So we're going to say 22.5 millimeters. We're going to come back here. Actually, we're just going to close that document, discard those changes. We're going to go back. Oh, wow. That's not... Close. All right. IMU mount. Sketch. We're going to come down here. We're going to change this to params.imu width. All right. And then we're going to say IMU mount height. And we're going to copy that name there. Set the alias of this cell. And then we're going to say, let's double check how big these holes are on the MPU. Great enough to be extra thick. All right. So, 3.25. We're going to measure the diameter of the holes on the MPU. They are 3.3 millimeter, which means these are M3 sized bolt holes. So the MPU, the threaded inserts that I have for M3 screws are 5 millimeter. They're 4 millimeters tall, 5 millimeters wide. So we're going to, so the smallest M3 bolt that I have is a 6 millimeter bolt. And so since we want the IMU to sit flush with its mount, and we want the IMU to sit flush with its mount, basically the thickness of the mount plus the thickness of the PCB needs to be at least 6 millimeters, since that is the shortest bolt that I have. And the width of this PCB is 1.6 millimeters, which is a very, very common thickness for PCBs. So that means we need to make the mount 6 minus 1.6, or at least 4.4 millimeters tall, but just to give ourselves a bit of margin, we'll just make it 5 millimeters tall. So make that 5 millimeters. So we're going to leave this sketch now that it's fully constrained. We are then going to turn this into a pad, which basically extrudes the part, essentially. So we're going to put pad, turns into a little brick. We're going to say parameters.imu mount height. All right. Perfect. And then just so we know where this thing is, we shall... bottom. All right. Then, just so we know how we're mounting it on this, we're going to say transform this. We're going to just drag it up here. This doesn't actually do anything particularly other than let us know how it looks like. All right. Just say OK. And then now we need to place the holes. So realistically, we want the MPU centered in this mount. So let's measure the horizontal length here, which I have been calling depth in this spreadsheet. It is, let's see, how thick are you? It is 16 millimeters thick. So we will, or in the parlance of this spreadsheet, it is IMU depth is 16 millimeters. Depth, all right. So that gives us the thickness of the IMU. So that means we need to center the IMU, we need to center this 16 millimeter long thing on the 40 millimeter long mount. Right. All right. So now we also need how much are the screws offset from the center of the IMU? So what is the center line of these screws, essentially the center line of the IMU chip? And so Using my Mark 1 eyeball, I say that there is about a... let's see here. Trying to use the calipers. Let's say there's about a 5 millimeter separation between the IMU. There's an offset between the screws and the IMU. So we're going to say IMU bolt offset is 5 millimeters. Copy this name again, set the alias. This alias is what we're actually adding when we say parameters dot something in the drawing. So we're going to do bolt offset, and then we're going to do IMU bolt diameter. We measured that at 3.3 millimeters before. Although this doesn't really... IMU bolt diameter. We don't really care about that number too much. Realistically, we just want to know the hole placement for the IMU. So we're going to measure since we're going to start with the outer measurement of the bolt holes, and then we're going to measure the inner measurement. So the outer measurement is 18 let's see, 18, looks like 18.4 millimeters. Oh, I got a little angled. It's about 18.4 millimeters on the outside. So we're going to say IMU bolt spacing as 18.4 millimeters minus the inner is 12 millimeters. So 12 millimeters. So actually, we want the average between these two, essentially. So plus 12 divided by 2. All right, I put an equal sign in front of that. All right. Oops, sorry. Remove the tick marks. All right. There you go. So that's the IMU bolt spacing. So that means that they are, in theory, 15.2 millimeters apart. So if we set our calipers at 15.2 millimeters, they should line up with the centers of both bolt holes, which it appears to do so. I don't know how easy that is to see, but it lines up more or less. So let's see. All right. All right. Perfect. So then we'll save that. We'll go over here. I'm gonna add a sketch to the top. We're gonna turn off our chassis view again. We are going to add 2. Actually, we're going to start with adding a point to the center. We're going to define the distance here as that IMU offset. Parameters IMU bolt offset. All right. We're then going to put 2. We're going to constrain those horizontally of each other. We're going to constrain this vertically. Oops, nope, that's not right. Sorry. Constrain these 2 vertically with the... Nope, I did that wrong again. All right, sorry. So these are always horizontal. These are also horizontal. Perfect. All right. So we're going to constrain the distance here as parameters dot bolt spacing divided by 2. We're going to do the same thing over here. Do parameters dot bolt spacing. All right. Set that up there. And then we are going to constrain the radius of this. So that should be, I can't remember the shortcut. Dimension D. There we go. Since my threaded inserts are 5 millimeters in diameter. We'll set the diameter of this hole to be 5 millimeters. We don't have to do an equation for that. 5 millimeters. Do that. 5 millimeters. All right. And perfect. The last thing we need to do is cut out, or well, actually, sorry. And then we need to turn these into holes first. So we are then going to make these pockets. They're going to have a depth of the mount height. Okay. Perfect. Those are where our threaded inserts will go. And then now we need to cut essentially a trough along the backside, which is where essentially the pin headers will be mounted. So we need to measure the offset on that. The offset on that is, the center of that is roughly, it's roughly about 6.8 millimeters. So we're going to say IMU connector offset to 6.8 millimeters. Copy that, alias. All right. And we're going to measure the width of the connector, which is usually something along the order of 1/10 of an inch, so 2.54 millimeter, although we'll give ourselves just 4 millimeter just to make sure that we've got some margin. So we'll go here, we're going to go back to here, we're going to add another sketch. Now let's see the height, we're going to do a centered rectangle. We're going to put it here. Do that. I'm going to constrain the spacing to connector offset. And then we're going to set the height here to, as we said, we're going to give ourselves 4 millimeters for margin. Then we're going to import the external geometry of these edges and then bind the width of this rectangle to that. So go back to the sketch. I believe it is GX to import an edge, which it is. GX to import the other edge. We're going to do this. We're going to call it, did that wrong. Let's call it, I need the coincident marker. Constrain coincident. It does not like that. Okay, it might not be able to do line to line. We might be able to do point to line. Perfect. Which we can do. All right. Then we close that sketch. We then make a pocket. We don't want to cut the thing in half, so we are going to set the depth at something practical like, we'll just say half the height. And what's a soldered connector is usually like 2, but we'll do 2.5 millimeter. About half. Actually, yeah, we'll codify this parameters dot depth, not depth, width, no, height. Can't remember parameters. IME mount height divided by 2. All right. So now we've got this piece of this thing where we can mount the IMU. It'll screw into these two holes. The connector will line up here. And just to actually kind of illustrate this, we're going to go look for an MPU 6050 model on Thingiver, somewhere at least. So we'll pull up our web browser here. We're going to look up MPU 6050 step model. All right. I don't like GrabCAD. Let's see if there's an open one. Actually, I mean, this does look nice. GrabCAD. A whole self-balancing robot. Look at that. Okay. 6050. Let's take this one. Download files. Let's see what the license is. Well, dimensionally accurate. We will take the step model. Download. Oh dear God. Drag it over here. Sign in. Right, sign in. Download that floppy. No, wait. Step model download. All right. Show me where that's located. Cut that. Go to our 3D modeling, step models, paste that here, and then we're going to import that into our enable stuff. Okay, perfect. Now we're going to recompute object because it wants me to. We're then going to transform that up to the top here, and then we're going to, because we're mounting this backwards essentially, we're gonna transform, we're gonna rotate that. Perfecto. Well. That doesn't quite look correct on the alignment. I don't know if this is dimensionally accurate. Well, anyway, let's make sure the offset on ours between the bolt holes and the trench are correct, which is 12-ish millimeters on mine. So as long as the center here of the trench lines up with the bolt holes, we're good. We're going to do a ruler. We know that... Okay, well, these holes are 5 millimeters in diameter. So that's going to be 7.3 plus 2.5, so it's going to be 9.8 plus 2. So that's 11.8, which is pretty freaking close to what I've measured here. So 11.8 is pretty much on point. So actually this MPU 6050 model that I just pulled off the internet is slightly different than the ones I actually have. So I'm not too worried here. So either way, okay, placement, we just want to bring this down. Oh, well. Arrow, translate the axis position, we want 5.2, 0.4, 0.6, all right. Close enough for me. All right. Not that actually matters. This is for prettiness. All right. And then the final piece that we're going to do is we're going to make little ears that come off the side, just so it'll it's easier to align on the robot. So we will do a sketch on this side. Apply sketch here. We'll do a centered rectangle here. We'll do another one here. All right. So we're going to import external geometry. This point, we're going to import external geometry. This point, we're going to make these 2 points coincident. We're going to make these 2 points coincident. We're going to define the width as grams IMU height divided by 2. Let me do the same to the other side. Grams IMU mount height divided by 2. All right. Perfect. Close. We're going to then extrude those. We're going to pad those essentially. Those are going to be rams dot IMU mount width. Why aren't they showing up? It's probably because they need to be slightly... Interesting. Maybe it actually has to intersect the model in order for it to do anything. Pad. Oh, maybe it's because it's going to come out. So maybe if we extrude it, pad in reverse. Maybe that's what we have to do. Direction. All right. Pad. Pad. No, that's not right. True. Oh, delete the padding. Sorry, we're gonna try that again. Pad, reverse. Yes. All right. Perfect. Parameters. IMU mount width. Perfect. Okay, we got a little ears. Nice. All right. So we got our little IMU mount. We'll stick our 2 threaded inserts in these holes, and then this will then, if we go back to our body, will then essentially sit, over the mount over the edges of the frame. We'll just super glue it on because it's just test frame. Stand, battery, visualize all our stuff. All right, so we'll have we'll turn our MPU as well. Perfect. So that is what it'll look like. So let's print out our little IMU mount model. So file, export as balancer IMU mount. That'll go in STL. Okay, nice. Save, close, save that file. All right, and then we open up Bamboo Studio. Then prepare a model. We'll take our step model we just exported. Modeling, STL. Ah, that's why. Wasn't there. IMU mount. Oh, nope, not stand. IMU mount. All right, cool. So it's in the center. To make it, we'll actually print it the other way, but then it would be slightly lumpy. You know what? I don't care. So we're gonna make this. We're gonna do that. Perfect. That'll be a lot easier to print. We're gonna print that out of green PLA because that's the rest of the robot's printed out of. Alrighty, so let's kick this off. So slice plate, it will take it, well, it's going to take it 5 minutes to level possibly, so up to 15 minutes to print, which is literally nothing. Strength, I'll just do bottom shell layers a lot too. Alright, gyroid. This doesn't have to be strong. Yeah, we'll just do the easy one, grid, like it had before. Slice plate. Look at the insides of our little model here. We'll just how much easier is gyroid to print on top of? Bottom. Sorry. Whoa. Gyroid. Slice. Anywho, all right. So we're gonna do that. Print. Put on my P1S. To send. All right. All right, and we'll come back to the printer when it's done printing. So, back to programming. Okay, so if you haven't downloaded the code, if you want to follow along with the program for the balancer, I've uploaded all the code to github.com/technomem17/Pico balancer. The link is in the description. So let's go back to what we need in some code changes anyway. So let's start building our tool, right? If we, while we're waiting for this to print, there's a couple things that I thought about off stream that we should do better on. And first of all, that we are actually doing our IMU processing inside of the network loop. And the reason that this is bad is I found out when I was trying to demonstrate it to somebody the other day that if there is any sort of hiccup in the internet connection the Pico W has, this send function will hang for a little bit, which means we stop updating our balancing. So the robot, you lose Wi-Fi, the thing just falls over. So we're going to not do that anymore, and we are going to move the what are we doing? We're going to move the balancing up into the IMU task. So the first thing that we're going to make a function that does essentially the balancing computation. So the first thing that we're going to, all right. So the first thing we're going to do here is compute balancing, or I should say update mode. Well, actually, we'll just say update motors. And we'll give it a reference to the orientation from the IMU. So we'll do vec3, we'll say const vec3 orientation. Oh, we started printing. Okay, cool. So we will take all of this previous error code and such and copy that. We'll bring it up here to update motors. Do that. We're receiving the orientation from up here, so we don't have to do that bit. And we're not going to do a while true. Oops. Alright. So now we need a way to move this stuff outside. Actually, do we want to do a function like this? No, I don't want to figure this out right now. So we'll just cut this into here. Say PID constants. PID state. Actually, all right. We'll take this, delete that function. And this then feeds to the queue, so we don't have to worry about that. I change all of these orientation to Euler, which we don't have to worry about. Send orientation to network thread. I should say send. Actually, because we're going to do more than the orientation, no fall over on Wi-Fi loss is a safety feature. I don't know. It depends on what it's carrying. Send state to the network thread. All right. So some previous error. So actually, it's probably best that we call some error what it actually is, which is I. So we're okay. Some error I. All right, so that should work. The other thing that we're doing that's not good is imagine that the I value essentially is that this response exceeds what the motors can actually do. So, for instance, if we go to this left speed here, we already clamp, or we do what's called clamping, which is if the speed exceeds the maximum value we can set, we set it at the maximum value. We're limiting what it can be. So the problem is that it's not really desirable if this control input goes beyond that, because then we're just cutting the result. It also means that we have, so it's a PID, general PID controller problem called I windup, or error windup, which is if the controller is trying to push harder than the machine can physically go, you know, a good design will limit the control output to what the robot can actually do, but it'll still keep building up this error value. So the problem is that if the error does start coming down, you will not react to that decreasing error because you have this just immense integral constant steady state buildup, which is bad. So there are multiple techniques that you can do to limit wind up for the I value, but one of the easiest is, I don't know if this is the actual name for it, but I've always called it backpropagation, which I know is also another term from AI training, but basically what you do is if you detect that the output of the PID controller exceeds the maximum value that the maximum control output, you then you calculate what I would be required to hit that. Basically, if P plus I plus D exceeds the maximum control output, you then compute the I value such that the output would equal the maximum. Because you know it's going beyond, and you would just clip off that value to maximum anyway. So recompute the I value such that it will still be maximum, but only just maximum. And up to maximally zero out the I value. So, so what we're going to do here is we're going to add our backpropagation on the I value essentially. So if so we're going to start by saying float response equals KP times error. Actually, wow. Okay, sorry. Response PD for proportional and derivative. So we're going to say KP times error plus KD times the derivative, which is the error minus the previous error. And then response is essentially this response PD plus KI times I. All right. And the way that I had set this up before response times equals motor wrap is that this motor wrap is 5,000. So we're assuming that this PID controller is outputting between -1 and 1. -1 will be motors full reverse, +1 is motors full forward. So we're basically trying to say, if the response is greater than 1, we need to figure out what we should do. Greater than 1 or greater than negative, or less than -1, figure out how to limit the I value. So what we'll do here is if response is greater than 1, else if response less than -1, then we need to do stuff. So if response is greater than 1, meaning we've exceeded how much we can turn the motors forward, we will basically do hold on. I equal, no. We'll then check if response PD itself is greater than 1.f. Essentially, we've overwhelmed whatever the I value could be anyway. Actually, I could be negative. So, sorry. Say, actually, if response PD is equal to, it's greater than 1 itself, we'll just say I is equal to 0, else I equals response, we'll say 1.0 minus response PD divided by KI. Because basically we're going to be multiplied by KI anyway. So I equals 0, I is response, and then anyway we're going to do response equals 1, point F, So if response PD, so if the response and the proportional and the derivative already max out the system, we're going to limit the I. Actually, I wonder if it would be better to not delete I, but then basically compute the I such that the value. We'll experiment with both. Actually, we have a robot. We should see what happens. This is a learning experience. All right, so if the response from the proportional derivative itself would exceed the control output, then 0 out I. Otherwise, compute I such that the result would be 5,000. Essentially, I, if you do times I times ki, would then be equal to 1 minus response PD, which would basically be whatever else, or 1 minus response PD, which would be the remaining portion. Okay, so then we do if response PD less than 1.f, or negative 1.f, then I equals 0. Make sure to put I float point f, else I equals negative 1.f plus, hold on, response PD is some negative number, so minus a negative is a positive, so it's still minus response PD divided by ki. That's right, because if this is like negative 0.9, then we would have negative 1 minus negative 0.9, which would be negative 1 plus 0.9, or negative 0.1, which the two of those added together would be negative 1. All right, so we'll do that, and then we need to limit our response output to negative 1.f. All right. So then we take response times motor wrap. All right. Input error, and then we'll update balancing, compute input error, compute angle error. All right. Move that down here. Sorry, is nan previous error there? Plus error. All right. Previous error. We don't need that after this, so update balancing. And we'll do this update balancing, PID controller, and then we'll say update the motor values. PW motor inputs. Motor inputs, this is backpropagate. I wind up. Backpropagate to solve I wind up. I term wind up. Alright, so we got this. XQ send, Euler, Bueller, Bueller. Alright, so we got this. PID constants. Send to the network thread. Now we delete all this stuff out of here while true. Receive the next thing, and then we just print out. Oops, sorry. Let me just compute the. So yeah, we don't have to worry about response. All right. This should compile in theory, right? Yes. All right. Perfect. So that means we will still kick off the MPU thread up here. Print out, do the connection. So we should start balancing almost immediately, essentially. All right, so we're limiting the I wind up. We're doing that. Okay. Perfect. I think I did that right. Yeah, yeah. All right. Well, anyway, we'll test on real hardware here. Let's plug in the debug adapter. Make sure we got this the right way around. right. Just going to power up the logic for now. Okay. What do I do with the other battery? There it is. All right. We're then going to up-flash the project to our balancer. To the 6 people watching, thank you for watching the stream. If you have any questions, comments, or anything, please just leave it in the comments. I have the comments up on my other screen here, so if you have any questions, want me to explain something in more detail, just drop a note. I'll try to respond. All right. So we flashed to the robot. We'll then power up the motors. Switch to the desk cam. Wake up the desk cam. Alright. Actually, let's turn off the light. It's not dark. Alright. So, this should be the same. More or less. Yep. Alright. Well, we're still having that. It's being pushed around, though. Alright. So we can still balance, so we didn't break anything, probably. I don't think so, right? Yeah. Still balances, more or less. And sometimes it goes away, but that's because it doesn't know how to stand up, really. It doesn't know how to stand up. It doesn't have any control to keep it in place, but it just tries to stand up. All right. So, I mean, we still have that wobbling problem. We're hoping to solve with the print, which is almost done. All right. Oh, let's put this back down. Desktop. All right. Power down the motors. Pulling this battery. All right. Perfect. Over there. All right. As we're still waiting on the NPU. We got one more thing we can change. So before, if you remember in the last stream, we used this semaphore logic to wake up, we used the semaphore logic to essentially signal the interrupt on the IMU. But there's actually a more performant way of doing this that was reviewing the stream was literally sitting right in the documentation in front of me. So if we actually look at this semaphore list, we create semaphores. Task notifications can provide a lightweight alternative to semaphores in many situations. So if we click on that, and we look at task notifications as a counting semaphore, turns out we can just use this much lighter mechanism, so it might be a little bit less latency. I don't know how much it actually help us. But might as well try. We might as well see what happens. So we're going to replace a semaphore with a task notification, which essentially, rather than having this semaphore object that we're waiting on, we just have the what do you call it? The task will go to sleep, just in general. It'll pause, and you can have something else resume its execution via its task handle. So all we really should have to do here is move this task handle structure and bring that up here to task IMU, and we will eventually delete that semaphore. And queue handle, create the task, IMU task. Okay, we'll delete IMU sem just to test this. Looks like we finished the print. All right, we'll go grab that in a second. And then put the task up here, delete semaphore handle. So instead of this, if IMU sem, this is a pointer, right? Yes, that is a pointer. All right, so task IMU will just say equals null pointer. Wow, I can't type today. Null pointer. If task IMU, then what we shall do instead is vtask notify give from ISR task handle or sorry, task IMU, and X higher priority task woken, and port years from ISR. And let's actually see if this notify give from ISR checks for a null pointer. No, it will just assert and die. Okay, never mind. We have to check it ourselves. Alright, so if task IMU, then we give it. Otherwise, do that thing. I'll do the DMP enabled queue semaphore take. We'll then replace that with notified take, notified value. We don't actually care about notified value really. So we'll say ul task notify take PD false, and block time I believe is PD port delay sorry, is PD something max. It's something max delay. There we go. Port max delay. All right. I think that's pretty equivalent to what we did before. Yeah. Notify take. PD false. What is that first argument? Default index to notify, which is block to wait here. V handling task. Query peripheral. Process peripheral event. V check for error. All right. Cool. That is fine. All right. Wait until the MU interrupt has been triggered. Get a packet from. Actually, what we'll do here, just to make this a little better, we'll say we're gonna check the FIFO. We're gonna first. What we'll do is we'll check the FIFO length of the IMU. If FIFO count less than packet size, then what we do is then we wait. Then we wait for the test delay. Basically, if there's nothing to do, then we wait. Otherwise, we just come through here, and we really probably ought to just check MPU int status ourselves at some point, but this is still mostly lifted from that piece of code. So if we do what's called, so then we want to recheck the IMU count, and then if FIFO count, packet size. Then if we were spuriously woken up, we then go back to sleep. Right. All right. Cool. That should be generally equivalent. Okay. All right. Save. Let's check whether this compiles. Project. Oh, nope. I did an oopsie. Ah, I declared it twice. All right. Sorry. We'll FIFO count. All right. Compile project. Cool. That did. We'll reflash this. Flash plus WD. All right. Let's see if it still balances, because that's really just the benchmark we have. All right. Let me just do this over here. Well, it still performs exactly as it did before, which means we didn't break anything with that change. Perfect. I don't think it's balancing any better, realistically. All right. So, that change is valid. All right. Just turn off the motors. All right. Turn off the motors, and I'm actually going to turn off the logic, just because we are going to install that new IMU mount. All right. So, we got Those are taken out. Put that there. Those calipers. All right, let me switch over to the desk cam, and let me turn on the desk cam audio. Input again because my desk mic is a lot better than the phone. All right, we're gonna keep. All right, it has been years since this was mounted, so this sticky tape is gonna be literal glue. It's not gonna be the fun kind of though. All right, cool. Do. There we go. IME removed. We'll clean up. Try to clean this up. Without doing too much damage to the underlying PLA. Don't push on the knife when it's in front of my fingers. Okay. Yes, Hassan Rasid. Okay, yes. I am using I2C for the 6050. I believe the 6050 only supports I2C mode. It's the NPU 6000 that supports SPI. Actually, it might just be easier to use my fingers to pull this off. Aye. Ugh. Aye. Probably about as interesting as watching paint dry right now, sorry. Alright, almost there. Trying to get this off, otherwise the glue won't stick. Just broadcasting my thumbs trying to roll off sticky tape to the internet. Alright. Alright, that looks pretty good. Ugh, on out of focus. There we go. Alright, that looks good. I got sticky goop. Alright, one last one. Take the IMU off. Looks like I'm in the same problem here. Oh dear. Ah! Ow! Hey. Alright. It's removed. I'm gonna sacrifice a little bit to the gods of electronics. Currently paying for the shortcuts I took in years past. Well, when I first did this project, I didn't own any threaded inserts, and I really wanted to test it out. But then, you know, I never finished it. Now I'm finishing on a stream. So, goop. Slowly remove the goop. Okay, almost there. Almost there. It's got sticky tape removal ASMR here, right? Alright. Hey, almost there. There we go. Alright. Oh, the double-sided tape removed. Perfect. So, now, this actually mounts in the way that I hoped it would. Perfect. So, then what we'll do... the MPU will sit in here like this, and the screws will line like that. Perfect. Perfect. So that'll go in there the way that we want it to. Let's measure some points on the robot. So... grabbing a Sharpie. Alright. I'm grabbing a Sharpie. So, this thing came out to... 22.45 millimeters wide. We told it to be 22.5, so it's pretty dimensionally accurate. And not the best, not the worst. So, if that's 22.5, we're still zeroed out. So measuring this robot inside here is 125.88. It's really supposed to be 126. So we'll do 126 divided by 2. which would be 50, 60, 63, right? 63 would be 120 plus 6, yeah. So 63, so we need 63 millimeters from the edge is the center. So that's here. But because this thing is 22.5 millimeters, we need to subtract 12.25 from 63, which would be, or no, 22.5, so that's 11.25 millimeters. Okay, so 63 minus 11 would be 52. It's going to be 52.75 would be the edge. So 52.75. All right. So that'll be here. 5. All right. Do the other side. 2.75. All right. Perfect. Oh, God. Sorry. All right. Now we're going to bring in super glue, which, if any of my super glue usage is anything to go by, it's going to end up all over my fingers. I can never use this stuff without it getting all over my fingers. All right. But that is a me problem, not a y'all problem. So, we will take some Gorilla Glue. Gorilla Glue is really good for PLA because it will actually slightly eat the surface. Alright, and it will slightly eat the surface, making it a really good binding agent for 3D printed parts. At least 3D printed parts of PLA. So, we're going to do that. We're then going to place our little IMU mount. We're going to center that as best as possible, which it looks like we did. I'm going to press these two surfaces together per super glue instructions. Alright. Those are never going to come apart again, presumably. All right. We'll let that sit there for a second. I'm going to put the glue away and go grab some M3 by... Uh-oh. Something broke. Oh, it's back. All right. Okay, and, sorry, what was I going to say? Right, put the super glue away and grab some M3 by 6 bolts. Which I have in this fun little package here, M3 by 6 millimeter. They are Allen keyed screws. Oh, look at that. Ow. I bled for this. Alright. Okay. M3 by 6. Oh my god, there's so much oil in here. Ew. Alright, 2 bolts. Grab the right Allen key. Nope, that one's too small. Alright. I need the 2mm wrench. Alright. Is that one the right one? That one's too large. What the heck? Hold on. I must have got these mixed up. Hold on. Yep, I did. I grabbed the 2.5. Alright. Alright, here's the 2. Alright. Here's hopefully the 2mm. Alright. Yes, perfect. Alright. So, now we're going to insert the bolts for the IME. Uh-oh. Uh-oh. It looks like these might be too large. That's unfortunate. Yes, they are hitting a capacitor. Okay. Well, that rots. That one's good. Who the fuck? I put an M3 bolt and then just... Who designed this board? Then do the right keep outs for M3. Well, that rots. Okay. So now I don't know if this is better or worse than we had before. Realistically, I don't know. I don't know. Okay. Here. I'm assuming that's a short. That would be a. Okay. You know what? Maybe. Let me just try to get some light in here. Okay. I'm guessing that's VCC to ground. You know what? Let's see if we can get this in here without shorting it. It might be fine. Because if it just sits on top of one axis, if it only sits on top of one pole, it's probably fine. If it sits on top of two, then we're screwed. Not screwed, but we can't put this... This bolt will be unscrewed is what will happen. Yeah, it's really looking like this is going to come down on both sides of that capacitor. Alright. Why does this keep dropping out? I'm sorry. No, actually, we might be fine. We might be fine. It might be tearing off that. Oh, no. Oh, shit. Alright. You know what? We're gonna... I knocked that capacitor off. Oh, crap. So, can we relocate that cap? Actually, did it even... What did it do? What did it even do? It pushed it, rolled it back, which is bad. Oh, there's a 1.8 volt regulator, I think, right? I think that's what that is. Because I'm running them off of... Actually, am I running this off of 5 volts or 3.3 volts? I mean, I know there's a... I am running this off of 5 volts, so we need that regulator. Shit. Alright, well, in order to prevent further damage, I will just not continue doing that. No, don't touch the super glue. Alright, make sure that I've aligned the other bolt hole. Something. Alright, cool. We're gonna We're gonna have one freaking bolt holding down our IMU. Okay, that's unfortunate, but we're gonna have to make do. All right. I don't even know if that's a line straight. Okay, well, let me move this camera. I gotta. Sorry. Desktop. Okay, sorry. I need. No, stop. Okay. Sorry. Let me just make sure this thing is aligned correctly. I don't think it is. I think it actually is. Is it? Okay. Well, I guess I should have used M2.5. Okay. Either way, I think that is mounted as good as we're going to get it, and that sucks about that MPU. That's going to be the output capacitor for the voltage regulator. I really don't want to break that. All right, well, let's see. Let's see if it still balances anyway. Perfect. Okay, we'll power up the logic. And we'll power up the motors. Well, looks like it's still responding to stuff. Okay, I didn't kill the IMU. That's good. Although it still has that jittery mode. That's unfortunate. Here, let me... Nope, come back. Still little jittery. Still enter that really unstable zone. So that was not the IMU being loosely mounted. Okay, well, that was a colossal waste of time. Well, no, it's mounted better, but it's not a waste of time. It's mounted better than it was. Okay, well, on to the visualization tool. Let me just disconnect power from the motors. All right, we shall leave the. All right, turn on the light in here real quick. Okay. Okie dokie doke. Okay. Alrighty. Okay. Back to. Okay. Back to. Okay. Sorry. Let's grab a drink real quick. All right. So, if we go to our terminal, and we should have the virtual environment, right? Pico, SDK board, Pico, CD. Where's Python? Python stuff. Oh well. Alright, fine. Terminal will close. Alright, so at least let's add what we've got so far. Git add dot. Oh, git reset tools. Let's get commit. Legend CVP properties. Interesting. I don't know what I changed in there. Okay, other way. -m moved to task notifications and separated Wi-Fi from balancing logic. All right. Yeah. All right, so that bit of code's up there. All right, perfect. Okay, so if we source that virtual environment, VM bin activate, and then we do tools, UDP receiver. Oh, what? Pip install basic UDP. What? Hold on. All right, my Python virtual environment is not functioning as expected. Still not functioning as expected. All right, palette virtual Python. Right. All right. We should see. All right, pip. Something's not right about my. Something's not right about my virtual environment. Let me pull up a terminal. Hold on. Projects, ARM. Oh, you know what? You know why it's not working? It's because I changed where this folder's located. Okay, that's why it's not working. Perfect. Okay. Sorry, I moved some things around off stream, and so that is actually why it's broken. I need to recreate the virtual environment in here. Use Python here. All right, perfect. Now we can do our fun stuff. Some QDP, Jupyter, Boca. What? Actually, we are not in a virtual environment right now. All right, select interpreter, our virtual environment. Select interpreter, virtual environment. Right, right. That's what we did. Right. It should be there. Right. Should be there. Right. Right. Nope. Really? Why? Why is this not working? Oh, okay. We'll figure it out. We'll figure it out. Oh, now it looks like it's happy. All right. Yeah? All right. Cool. Pip. Yay. There we go. Just close it and reopen it a couple of times. Apparently that's how you get Visual Studio Code to do stuff. All right, now we have stuff. All right, tools, UDP. All right, awesome. We are seeing the data, the raw data coming from our balancing robot. Awesome. So now that we have, okay, so one last thing before we get to the visualization tool, I promise. Okay, I just realized something. So one of the things we didn't do before is actually calibrate the IMU. So if you remember in our balancing code, we have this pitch -3 degrees is our input to our balancing loop. Yeah, well, the reason that we needed to do that was because I didn't calibrate the dang thing. So let's actually go back to the I2C devlib utilities and actually calibrate the IMU. So we can close the 3D printer. Don't save. So we're going to create a new window here. New window. New window. Nice. And then we're going to open folder. Actually, we're going to go to Pi extension, import project. We're going to go to projects, ARM, I2C devlib, RP2040, MPU, examples, calibration. We're going to go to debug probe, enable CMake tools, Pico SDK, import. And this, like all of the other stuff we were doing before, is probably not going to build because the CMakes in here were broken and looks like it's the same thing. So we're going to, let me just zoom in here for you. These are not in the right directories, right? So we're going to just open the fix that we did for the other tool and just copy over those changes. So we will add these two files. We will then add these include directories. I'm just going to make it the same as the other one, even though I don't like how it does this. So MPU calibration is the name of that project. So DMP port. I think that's the only thing we had to move over. Pico standard lib. Why did that change? Oh, it's just a trailing space. Okay. So that should let us build that project. So compile project. Output. Well, something's happening, presumably. Let's go to our CMake integration, which doesn't look like it loaded, actually. So let's close that window, reopen that window. Ooh, delicious. We're gonna... Is our CMake tools integration actually busted? Why? Why is that the case? Did I forget to select? No, I couldn't have. Okay, well, at any rate, we'll close that one. Close the folder. Pico. Import. Projects. ARM. I2C. RP2040. MPU. Examples. Calibration. Debug probe. CMake tools integration. Import. Compile. Wow. Wow. That's really not working. It's really not working. What the heck? Maybe it's not dot. Delete the build folder. We'll do that first. Activating extensions. Why is this one so broken? Why? Really? Really bored. Extensions are not activating. I don't like that. Don't like that at all. Well, open folder. No, sorry, new window. MPU calibration. I guess CMake isn't showing up over there either, you know. I don't want... Sorry, I have it. I'm trying to make it display. What the f... Okay, that configure CMake. An S to be. Okay, what broke? Why is this broken? Okay, hold on. We're gonna restart all the Visual Studio Code. Oh dear. Alright, CMake showed up this time. Perfect. New window. We're gonna open MPU calibration and no CMake. Maybe it'll build. Maybe I'm deluding myself here though. Compile. Yeah, deluding myself. It's broke. It's still not working. Wow. Why? Why is this? I don't even know how to debug this. CMake tools. Yeah. Alright. Yeah. That is actually really confusing. Okay. Why are you broken? Why are you? We're just gonna be a little tricker. Maybe the Pico SDK is stupid and can only have one thing open at a time. That would be really dumb. But let's try it. I'll close window. No. Oops. Close folder. Calibration. I'm installing Chef. Compile. Oh, that wasn't it. I mean, that's good, but that's also stupid. Why is this not working? Maybe we don't enable the Visual Studio Code extension. Maybe close folder. Maybe we import project. Don't do that. Okay, made it a little further. Okay, that's why. Needed on Wi-Fi to access the GPIO. So compile. Okay. It has to be reused. Perfect. Okay, so we have the calibration tool. That totally didn't take as much. That totally took a lot more effort than it really needed to. All right. So we shall plug in the USB with the batteries disconnected so I don't fry my computer. Okay. So we're going to plug into the Pico W. We're going to hold the boot select button. Let this come up. All right. We're then going to run the... Oh, look, the CMake extension started. Oh, my God. Flash project. Nope, that's not... That's usually what I do, but that's not what I want to do. Run project, USB. Okay. Serial monitor. Wow, we're almost 2 hours in. I still haven't got to the visualization yet. I'm bad. I'm sorry. All right. S0, start monitoring. ACM. All right. So, we're going to load this. We're going to watch it totally not work. Why? Oh. I'm an idiot. Okay. I need to load in the fact that I changed some of this I2C stuff. Okay. Right. Open file, up a directory, DMP port. Copy these, because we don't have the MPU on the default pins. And then we changed all of this set function stuff. All right. Alright, cool. Perfect. File, run project USB. Loading in a flash. I'm gonna monitor. Alright, start monitoring, switch to this. There we go. We're calibrating the MPU. All right. All right. While that's running, let us actually start on this visualization tool. So we're going to use a tool called Jupyter Notebooks, which is pretty common in like the scientific world. So, so we're going to reopen a new window, Pico Balancer, bring back up our stuff. We're not even going to have CMake. What? Okay, this is odd. Can I really only open one Pico SDK project at a time? That's so stupid. Alright, well, alright, fine. We'll close that for now. We're going to use a tool called Jupyter Notebooks. Let me just open this from the friggin' terminal. ARM, Pico Balancer. Alright, source, virtual environment, bin, activate. And we're going to go to tools. We're going to run Jupyter Notebook. That'll run Jupyter Notebooks. Bring that over here. We've previously had this IPI receiver tool, which is that UDP receiver we've been using. So if we bring that up, we'll just put this in the background. We'll do tool /UDP receiver. We should see, oh, right. We're not actually sending, the robot's not sending data, it's running the calibration. Okay, sorry. Just bring Jupyter Notebooks back. Okay, so we have this balancer tool that we've kind of been working on. But what we're going to do is we're going to add a cell above here, and we're going to use essentially a tool called Bokeh, which is a all right, so Bokeh, which is essentially a visualization tool for using inside of Jupyter Notebooks. Bokeh, Jupyter Notebooks sample. Alright. So basically just lets you draw random stuff on the screen. So I've already installed it. That was what I was using pip for. So using with Bokeh. File, output notebook. So I think the most basic thing I can show you. Okay, it would be. Of course, it's a Mac screenshot. Go back. Let's see. Yeah, there's some samples in Jupyter Bokeh here. Probably some examples. Right, Jupyter. Static plot. Alright. Bokeh plotting. So we shall start by including some plotting utilities. Bokeh. Okay, Bokeh's loaded. We will then add above. Call this balancer PID tuning. Okay. we'll just call this balancer PID tuning utility. All right. So then we'll go above. We'll call this. This is a markdown cell. This is start Bokeh. Got that. We will then, just to follow the sample, just so you can see how this works, we will then paste that, show that. Now we've got a handy dandy plot. We can do a lot more with this, or a lot more than this anyway. So the first thing we're going to do is we're going to write a little utility that will show the tilt from the IMU. So we're going to use... All right, so we're going to keep this figure, but what we're going to do is we're going to use something called a data source, which is... wow, I can't type. Source equals column data source, which is essentially just a helper class for managing data sets for plots. So we're going to call that data equals dictionary, x equals nothing, y equals nothing. That's fine. We're then going to write, so p is our figure, and we're going to just give this a title of balancer orientation. So we'll just call this balancer pitch. Balancer pitch. X-axis label equals sample number. Y-axis label equals pitch degrees. We're just going to give ourselves like an 800 by 480. What was that weird resolution they used to do? 800 by 480? Why not? Why not? We'll do that. And then we're going to add a line plot, which will do uses x and y as source. So this is our source. We'll just give ourselves a line width 2, and we'll just call this a blue line. Make it a little transparent. Alpha equals 0.8. We're going to say handle equals show. This is our figure. and then give ourselves a handle, because we're going to need this to update the data in real time later. All right. And then we can handle a show. All right. I did not do this right. You know what? I forgot to from bokeh.models import column data source. All right. So we have no data. So we're going to say time 0, y 0. Right. All right. Cool. Let's call that sample. All right. So we got the balancer pitch. And now we want to actually update it from the data that we're getting from the robot. So we're going to do our little async UDP thing here. And now let's look to see if the robot was so the robot is calibrated. Okay, so pausing on this for a second. We're going to come back over to the robot. So we're going to come over, and what we're looking for is in this old DMP port that we were dealing with, what we're looking for is setting these MPU offsets, essentially. So just to have these all in the same view, we're going to uncomment this. And then set the X offset to basically this first number, the first numbers of all of these, essentially, because it's trying to close in on the best value. So we're going to say our X acceleration is -387. Our Y is 1135. And then 975. And then the gyro is 106. Oh, messed that up. 106, 18, 7. 17, or where did I get that from? 18, right, no, 37, 134, 975, 106, 18, 7. Okay, 18, 7. All right, so then copy these back in our other project after DMP initialize. So we're going to close this folder. We're going to reopen our Pico Balancer project. That's suspicious that we're not getting our handy dandy. Now we broke our P. All right. Now this one's broken. That's just brilliant. Okay. Fitting extension. Okay, hold on. Full on close of VS Code. Reopen. CMake shows up. This build, something's messed up. Okay. Either way, after the DMP initialized, but before DMP enabled, we set up our offsets. We can then come in here, and we should be able to delete this bit. And the error should just be the pitch, right? Yeah. So I'll just compile that. No. All right, that worked. All right, so that should now, in theory, be able to balance. But we need to disconnect our USB. We then need to come back to our SWD debugger. Plug this back in. And we'll reattach the voltage regulator. All right. We'll then flash this using SWD. CD and NIT failed. Oh, that's unfortunate. Serial monitor. Why did that fail? It's plugged in though. Come on. Come on. Come on. Come on. Oh. Do that. Come on. Why did it not detect my debugger? That's suspicious, to say the least. I am white curious about that. OCD command failed. Okay, that's interesting. Well, we should see. There we go. Okay, nope, something happened. Alright, perfect. Now we should be able to do the SWD debugger. There we go. Wasn't plugged in quite correctly. Alright. Oh, balancer is reprogrammed. But before, let's just double check that it still balances, because that is critically important. And we'll just tie this off. We'll switch over to my phone camera. OBS back up here. Switch over to desk cam. All right. So, let's power on the motors. See if it's crazy or not. Okay. Yeah. Let's hope that it still balances. Looks like it does. Perfect. So even though we changed, so we did that calibration routine. Still jitters a lot, but we were able to remove that -3 degrees, which means the MPU is. Get back here. That was interesting. Okay. Well, that wasn't expected. That's new. That is very new. All right. Don't know what caused that. Strange. Wonder if it'll do that again. Want me to do that? I don't know. Oh, I don't trust it. I'm afraid. Very interesting. Well, at any rate. Weird. Okay. I don't think that might have just been a fluke. Alright, let's just go back in its little dock. Alright, back to the desktop camera. Disconnect the motors. Alright. Okay. Glad it fell forward and not and smashed all the electronics on the backside. Alright, I think that's the first major fall that I've caught for it. Alright. So, why did we need to go back to the code for the robot? Besides plugging those calibration values, because now that we have calibration, we have the calibration, so we don't need to do the weird offsets. Now, what we need to do is actually format this data in a way that we can bring it over to our visualization tool. And to do that, we're going to start using we're going to start, rather than sending text over our UDP connection, we're going to start sending, we call it binary data instead. So, we've currently been using this vector3 union to describe the orientation, but we need to send more than that because we would like to send the PID data as well. So what we're going to do is we're going to start defining we're going to use a thing called an enum class, which is essentially just an enum type. So we're going to say, we'll call it balancer, we'll call it motion packet type. And we'll make it inherit a uint32. And then we're going to have motion packet. We're going to have motion packet type. Then we're going to have unknown or invalid, which is going to be 0. And then we're going to have orientation is 1. Okay. And then we're going to say we're going to have a union. We're going to have, this is going to be motion. Actually, sorry. First of all, we're going to have a struct, and that's going to be called a motion packet. Then we're going to have, that's going to have a motion packet type, and then we're going to have a union of the different kinds of packet types. And so we're going to say one option is a vec3 orientation, which would be an orientation packet type. All right. So we're also going to define another packet type called a PID packet, PID packet, and we're also going to say using orientation packet equals vec3. Just give it a type. Struct PID packet. We're going to say we're also going to give ourselves a PID configuration packet. That's going to give us a float KP, a float KI, and a float KD. And we're going to have a PID response packet of float P, float I, float D, and float response. All right, and then we're going to say, we're going to give ourselves a orientation packet. We're going to give ourselves a PID response packet. PID response packet. PID response. PID configuration packet. PID configuration. And in here, we're going to define a PID response. PID configuration. Okay. Perfect. So, now what we're going to define all of these as a attribute packed. All right, I think we can just say packed. Packed means that it won't use any more. It'll pack everything to size regardless of the system's preferred orientation. So actually, this should be struct motion packet. I don't know why I did that. I'm mixing my C brain with everything else. All right, okay, motion packet, perfect. And so what we'll actually do here is we'll actually change the type that this queue uses to size of motion packet. And it'll dequeue a motion packet. QIMU motion packet and then rather than doing this sprintf thing, we're just going to straight up send packet. And the message is going to be a packet, and then it's going to be a size of packet. And we're going to need to... Okay, cool. Perfect. So, we're going to say that... we're going to say motion packet dot type equals a motion packet type orientation, and dot orientation equals Euler. Right, and then we're going to send a packet. Send packet. All right. We'll just do an initializer constructor. All right. So now that should compile, presumably. Taking packed member may result in unaligned pointer value. That's bad. Okay. Vex. I'll just ignore that for now. It's probably gonna be a bad thing. Okay. Pile. Flash project SWD. Perfect. All right. So now we need to modify our receiver program. We're going to use something called C-types, which will give us the ability to interact with raw C structures. So we need to go over to Python C-types, which is foreign function data interaction thing. All right, so I'm going to first deal with structs. All right, so we're going to do a Python class from C-type, import C-type. So class, everything that we just did. So orientation packet is, we'll say orientation. Orientation packet is a ctypes.structure, and it has fields equal to, just make sure I got this right. It's going to be ZXY, or yaw pitch roll. So yaw, that's going to be a ctypes.float. And then we're going to have a roll yaw pitch ctypes.cfloat roll ctypes.cfloat. All right, and then we're going to have a class PID response packet ctypes.structure. Fields equals p types.float I types.cfloat d c types.cfloat. All right, and then we need one more response types.cfloat. Although the response is just the three of them added together, so I guess that actually is kind of unnecessary. Okay, whatever. Compile. Flash. Okay. So then we'll just move that. All right, so I need to remember to do Python constants. Python constants. Oh, there's no such thing. Okay, perfect. We're gonna have a orientation packet type equals 1. PID response packet type equals 2. Actually, we'll just do it the other way. Packet type orientation. Packet type PID response. All right. Response. All right. So then we're gonna do a class PID, or we're gonna see motion packet internal types.union fields equal orientation C types. Actually, sorry. That's going to be an orientation packet. PID response is a PID response packet. And PID configuration packet. Alright, and then final one is class motion packet, C types. Dot structure fields equals type. That is a C types dot uint cuint32, and then a data motion packet. I'll actually call this motion packet data. We'll call this data and then C types dot nope. There's actually a motion packet data. All right, so we have this decoding system. Actually, that's a type 3 packet, and then we'll have a packet type unknown 0. Okay, motion type, that corresponds with what we've assigned here. Response, PID configuration, PID response configuration. Okay, all right. Perfect. All right. So now that we got this, we're going to say data address, and then we'll say, I can't remember how we actually, from contents, pi.contents types. I'm trying to remember how to convert bytes to bars, bar dot values, range, sorry, cast is a C byte times 4. Actually, how do I do bytes to, this is probably, hold on, this has got to be easier than I'm thinking. Python C types from bytes. Our header from buffer copy. Okay. Packet equals motion packet from buffer data. Perfect. And then we'll do print packet. Maybe that'll do something nice. All right. So now that we're presumably streaming all of this data, we're going to say tools UDP receiver. No async UDP. What? Do not load the virtual environment. We're in the virtual environment. Pip. On the global. Oh my god. Alright. Alright. Are you shitting me? Okay. We're just gonna open up another freaking terminal because this is just dying. Just go. No. Terminal. No. Run. Where's the freaking command palette? Hold on. Select interpreter. Do the thing. Do the thing. There we go. Okay. Underlying buffer is not writable. So we can do a from buffer copy. And we'll just do that. There we oh. Okay. Packet dot type then. Perfect. Packet dot data dot orientation. Okay, cool. Dot yaw. Okay. F orientation equals yaw pitch okay, that should theoretically be alright. Yaw. Okay, and we see if we rotate the robot, the yaw changes. If we roll the robot, the roll changes. If we pitch the robot, the pitch changes. Perfect. All right. I love it. Cool. We have a way of bringing this in. So we're going to do a new folder. We're going to say balancer types. From balancer types, new file, init.py. Take this UDP receiver stuff. See balancer, actually rename balancer. We're just going to rename this to types. Rename types. .py. We're going to take this. We're going to cut this. Go here. Types.py. We're going to do an import C types. Paste that stuff. All right. Then we're going to do a from UDP receiver. We're going to do a from balancer import types. Types import motion packet. All right, and then that should still run, right? Yes. Alrighty. Perfect. So, all right. Now what? All right, cool. So now that we got that, we're gonna come over here and we're gonna modify this to do a async def main, and then we will do a async UDP create socket listen. We're gonna do a from balancer.types import motion packet type motion, or packet type orientation. Packet type orientation. Okay. Socket create local socket. We're then going to do a, and we're going to define actually up here. So we're going to do that. We're going to do a, give ourselves a little function def add point. Actually, I'm sorry, we'll do that up here. I'm gonna do a point count. We got counter equals 0. Do a def add data point value, and then we're gonna say this is a global counter. And then a new data counter plus 1. Then new data equals dict x equals counter y equals value source dot stream new data push notebook handle. Actually going to do from boca.io import push notebook. All right, and then from here we're going to say data address. We're going to say a motion packet dot from a buffer copy data. Sorry, packet equals buffer copy if packet.type equals packet type orientation, then add data point packet.data.orientation.pitch. And then we're going to say await. We can do that. I got created. hold on. Stream new data. Oh. Hey, there we go. And then we can tilt the robot and see the data coming back. Oh, I love this. Okay. All right. We can tilt the robot almost all the way over. We can tilt the robot the other way. Tilt, 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 tilt. Shake the robot around. Tilt the robot. Maybe we keep rollover at 1,000 or 10,000 or something. Hold on, task canceled. Still. Ooh, I love it. Okay. And the funny thing is that what we're going to be able to do is we can put the battery back in and then watch it balance. We can see the oscillation in the orientation. So now I'm pushing it around on the ground. We can see it visualize. We are jittering substantially. All right. So now we need to add the ability to send the all right. That's cool. It can recover from doing that. All right. Oh, hey, look at that. Cool. Just put this back on its stand. Took the motor out. Took the battery for the motor out. Well, I gotta put a switch on this or something. Alright. Alright. That is neat. At least I think so. Alright, yeah, because we can stream it off. That is cool. I love it. Hi. So it's basically a stair step function now. Okay. Perfect. So now what we're gonna need to do is we're gonna we need to wrap this main thing in a what do you call it? In a sorry. We now need to give it some buttons for starting and stopping what's happening so that we don't have to what do you call it? Restart the server every single time. So we're gonna cancel that, and then we don't need to worry about that anymore. I'm gonna say should run is true while should run, and then await main say should run equals false. Just to start off with this. So restart the kernel. Do that, do that. Do that, do that. It's running. You can see the tilt. Then should run as false. But this keeps running because I don't think probably is capturing global. Should run. Maybe that'll help. Restart the kernel. No. Alright. We're gonna need another we're gonna need some kind of event signal to turn it off. I think Python async IO flag flag, I think. The event. I think event.set. Wait your task, wait event set. Okay, that's what we'll do. We'll say import async IO. So we'll say exit stop listening equals async IO dot event, right? Or is it capital E event? Event while not stop listening is set. Wait, main, and then we would say stop listening dot set. Let's remove that should run thing. All right. Cool. So we'll just restart the kernel. Run that, run that, run that, run that. That does this. That doesn't work either. Okay. Interesting. Do I just say await? Or stop? Oh, that didn't help. Okay. Interesting. Well, anyway, I do a Well, in the meantime, let's change the IMU to also report the PID output, just so we can start futzing with that. Alright, so we're also going to say send PID packet network thread. We're going to say PID response packet, PID response, I plus PID response dot P equals KP error PID response dot I equals I PID response dot equals KD times, I don't want to do that, error minus previous error. Let's say PID response dot P plus PID response dot D. PID response D response dot I. Okay. We're going to say motion packet dot type equals motion packet type PID response dot PID response equals PID response XQ send Q void pointer packet ID or PID packet. PD and we don't want any waiting ever. All right. Okay, cool. We got this. We got our send PID packet to the network thread. Okay, compile. I'll do our Pico compile project. This break on me again. Why? Why does this keep breaking? I really don't like this Visual Studio Code extension for the Pico now. Worked really good in the last video, but now it's not working very well, and I really don't know why. I didn't change anything about my host. What the heck? Not fun. Where's my little shemake tab? really, really annoying. Okay. Okay, why does just restarting it a bunch of times make it work again? It's so stupid. Okay. No. Alright. Perfect. We'll just flash this with SWD. Change how this works. Restart. Say add. And add orientation packet. Let's say import from balancer.types, import motion packet, PID, response packet, add orientation packet, global counter, plus. Oh, this is gonna be fun. Okay. Orientation counter. Value is going to be, sorry, it's going to be orientation dot data dot orientation, which is orientation dot pitch. We're going to have a PID counter equals -1. Add PID packet. I think line, let's see. P dot line X Y P source equals green. Oh, say red. Looks like it's PYP. All right. I don't know if there's like a y-axis too or something. Sorry. XP equals. We'll just do PID counter. P equals PID dot I plus PID dot P plus PID dot I plus PID dot D. Honestly, should probably okay. All right. First non-existent column. Ah, I see. XP. And must stream. Okay, lame, or not lame, but interesting. Okay. Actually, you know what? That's fine. We'll just do another data source. Source PID equals column data source equals dict XP. PID is equals figure. Source equals source. PID. All right. All right. So. Ah, yes, because the way that it works is right, because that's the PID response. Let's see if it's possible to render two lines, or two, I call it two, a left side and a right side. Bokeh figure 2y axis, twin axis. All right, cool. Your y range, scatter, y axis, extra y ranges, foo. -1 to 1, extra y ranges. Extra y ranges. Maybe that's what we can do. Raspberry Pi. PID equals this is range. A range and pi. Ugh. Range 1D. Okay. Models. Say range 1D, 1 to 1, -2 to 2. All right, that looks like it worked. All right, so what we would do is line y range equals PID. Right? Y range name is PID. Y range. Wet. What? I'm confused. What is that? Why is that? Is there any automatic ranging on twin axes? Oh, I don't want to feed it an explicit range. Extra Y ranges. Not really what I want. So we'll just do 2 plots for now. Why not? I don't really want to deal with this. All right, so we'll just do that. We'll do P PID equals figure title PID response axis label equals sample y axis label equals response width equals 800 height equals 40 equals PPID. Can I show an array of the thing? Hold on, sort. No, you can't do that. All right, maybe if I don't do it as an array. I mean, I can always just do 2 different calls too. I don't mind. Yeah, no, I can't do 2 different. Okay. Handle PID. Show P PID. Notebook handle equals true. Oop. Okay, restart the kernel. Doop, 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 doop. Uh-oh. Oh. Crap. Restart. Alrighty. Response is 40. What? Hold up. That's doesn't make any sense to me. What the shit? Okay. I must have broke something. Hold on. this thing even still balancing? I don't even know. Here, Answer is no, it is not still balancing. Okay. I broke something. I definitely broke something. Okay. Alright. Definitely broke something. Alright, so I plus equals error. We're going to do P, or float P equals float D. Error minus previous error. I plus equals error. E plus D. Alright, const float P, const float D, there's error. Once. That doesn't seem to be moving at all. What the hell? Okay, now it doesn't seeming... No, what? Alright, hold up. I guess we can always use this to debug it. What the heck? What did I break? Orientation's still right. Something else is very wrong. X. Show X, we'll show all these separately. Alright, Y, P, line, what's that? P line, I line, D line, I, Y, D, red, that. YD equals D. Alright, so we're going to restart this. Do that. Do that. Alright. Green line is the derivative line. It's previous error minus equals error. So nan error previous error. And that is weird. KD is 1. 1 times error minus previous error. So why is previous error never set correctly? So we're going to just actually do a debug on this. We're going to do a debug Pico balancer. We're going to go into debug, Cortex debug, run the debugger. Alright, so here is nan p I plus error oh. That's probably what happened. Okay, Pico debug. Right, green is I, not anything else. Okay. Okay, there we go. Now it seems to be a lot more happy. Okay. Balancer. Looks like, oh dear. Alright, so we're seeing our real-time PID responses. We got a lot of eye wobble. It's been 3 hours. Okay, well, so it's balancing pretty happily, but a little jittery. So I wonder what's going on here. You know, somebody at the Robotics Club the other day mentioned, yeah, sorry, I haven't said anything in a while. So, somebody at the Robotics Club mentioned that one of the things I could be experiencing is just backlash on my wheels. Or on my drive motors. basically, the gears, when they're turning, there's a little bit of, if you've ever seen, if you don't know what backlash on a gearbox is, it's when teeth on two gears don't mesh perfectly. They mesh. I mean, the closer you get, the less backlash there is, but the more friction you get, which will reduce the longevity of the gears. So most gearboxes have at least some amount of backlash, which is basically backlash being the amount you can rotate the gearbox without the motor actually turning. Basically, the chatter, the how much you can rotate a gear without it actually pushing on the other gear. And these motors have a notable amount of backlash. Not a ton, but some. So the some of the jittering could easily be a result of that. But let's see what happens if we now that we have this beautiful little graph running of the robot balancing, let's actually add a utility for us to let's add a utility for us to change the constants on the fly. So we're going to need to add another thread to the balancer to listen for configuration updates. So eventually we'll do we'll try to use the widgets library in Bokeh here to be able to submit changes to the configuration. All right. So we're now going to let me disable the motors again. There we go. Plug the debugger back in. All right. And then we're going to add a new thread to the... So what we're going to do is... okay. Sorry. All right. So what we're going to do is change these we're going to add another thread, basically. Let's see. We're going to call it the configuration task. Unused. All right. It's called the configuration task. And as these can't exit, v task delete null putter. All right, so we're now going to want to listen to data. Connect to address. Actually, we don't want to do that. We sort of do. Queue receive, send. Check if any packets were received. Which, I mean, that's effectively a send only. Packets were received. Okay, actually, what this can do for us, actually, we're going to listen on a different port. That's what we're going to do. Sorry. We're going to say socket so what we're going to do is we're going to copy out this stuff. Connect. Also, the irony is, actually could go up a lot higher. All right, sorry. So we're going to copy this UDP socket logic, bring this up to our configuration task, receiving socket, receive socket for configuration. We're going to listen to, actually, honestly, we're going to do a res bind sock name. Where does this go? LWIP. No. Do. Alright, hold on. LWIP, free RTOS socket, listen any adder. Okay. Let me find that. Which tone is this? I mean, LWIP free RTOS. Adder, H-ton L. I forgot about that. H-ton L. Oh, hey, look at that. Syn port address dot syn adder. Oh, alright. There's another thing configured right. Okay. Syn adder is H-ton L in adder any. We'll just put this on port. Yeah, 3000. Why not? Let's rest address dot syn len equals size of address. All right, bind is yeah. I can kill that. Oh, that's adder. Alright, and then bind sock struct. Adder address as of address. Failed to bind. Receiving socket failed to bind. Configuration socket. And close sock. Test delete. No footer. Okay. Then we're going to. Alright, so we've got all this shit. We've bound, so then in a loop we can just receive stuff. So we're gonna say auto, so we're gonna say res equals rec v sock into actually rocked PID motion packet packet size of packet 0, I think. If res less than 0, res encountered an error equals %d res, okay, and then continue. Otherwise, do something, if packet dot type not equal, actually, switch packet dot type case motion packet type configuration do configure PID break default break. All right, perfect. It's probably going to be pushing constants somewhere. All right, so what we're actually going to, actually this is kind of evil. float. I'll actually just put the freaking constants up top here. Float. Volatile. Alright. That's kind of gross. Realistically, that is pretty freaking gross. I can't believe I'm doing this. Alright. Delete the constants from here then. And then, if, say, kp equals packet dot kp ki equals packet dot pid configuration dot ki equals packet dot pid configuration dot kd. All right, and that should update our constants live on the fly. It's kind of a horrible way of doing it. We should do some kind of synchronization mechanism, but I'm lazy at the moment. So we're going to then kick off the configuration task after we have our network up. So we're going to say task handle configuration task. Or am I calling things task? I mean, yeah. Task configuration. We got X task create. Say task configuration name configuration task. Configuration thread. Stack depth is, we'll just give it 8K again, and I'll put her. It's probably bad. Configuration task. Oh. All right, compile. Oh, I messed something up. What did I mess up? Uh-oh. Cool. All right. And they are all Flash project. Actually going to put a breakpoint on our configuration task. We're going to launch Pico debug. All right. Perfect. Go to the terminal. We're going to go to our. All right, already satisfied. Cool. So tools, new file, UDP, set PID constants .py. Take UDP receiver, copy that into here. Motion packet type PID configuration. All right, so I'm gonna say create socket remote adder. Going to be Pico balancer local port 3000. And then we're going to say we're going to need to decode command line parameters. All right, Python parse command line arguments. All right, easy arg parse, import arg parse. All right, so we're going to say KP equals one of the defaults. I'm going to say AP equals 0.2F, KI equals 0.025, KD equals 1.1. Okay, we're going to say packet equals motion packet. Actually, ID equals PID configuration packet dot PKP equals KP packet dot KI equals KI packet dot KD equals KD. All right, and then we're gonna say actually that's just data. It's just configuration, actually. Configuration. And then we're going to say data equals motion, or sorry, packet equals motion packet, packet dot type equals packet type PID configuration, packet dot data dot PID configuration equals configuration. All right. And then we're going to say data equals packet dot motion packet to okay, hold on. Unc types convert to bytes. How do I? Oh, I just do that. That's easy. Bytes. Packet. Ah, perfect. All right. Now we're gonna say await a sock dot send to data or bytes packet. Cool. All right, and so now we do our arg parse. Yeah. Parser equals arg parse dot argument parser. Prog equals configuration setter updates Pico W balancer PID configuration. All right, parser dot add argument dash p AP parser dot add argument I parser dot add argument dash d. Ah. Hey, all right, so add argument. So then we've got run main AP equals parser dot k dot p parser dot I d parser dot d, right? Oh, e k I k t. All right, perfect. Argument, is there a default? Argument default. Parser, add argument. Oh, and args, foo help. Parse args. There we go. Default equal 0.2. Default 0.025. Default 0.01. 1.1. All right, cool. So we got this little script running. We're gonna look at our Jupyter notebooks. Still doing a thing. Why is the previous error at -40? Oh. All right. Well, I mean that's just the I term. That's not the D term. Okay, cool. All right. All right, so now we should be able to do tools. Oh, change mod. So X tools, set PID constants. PID constants, attribute parser is no argument skp. Parse add argument. Did I do something wrong? Did I do wrong? Dash count. Oh, args is parser args. Oh, okay. All right. Let's see what happens. Hey, it went over. KP, KI, KD. Awesome. Okay, we have a Python script that can set the constants. Perfect. Okay, so if we were to say KI as 0.1, then this I term will be able to grow a lot. Oh. It's supposed to be a real number, not a string. Well. Oops. Okay. There we go. You see the I term completely collapse. Usually it's 0.25. So the I term can only be a lot smaller because it'll generate a lot more of an effect. So if we do 0.00025, this value is going to grow substantially. Yup, there we go. There we go. All right. Change the I term here. Dunk. Look at that. Look at that. We are able to set the configuration over the network. Oh my god, perfect. Okay. All right. This is good. This is good. That took a while to get here. All right. So, let's stop the debugging and reboot the CPU. All right. Let it start balancing. Alright, so if we set the D term to a lot less, let me set the D term to like 0.5. See what happens. Yeah, it just weeble wobbles a lot more. And now yeah, the D term is a lot more active. I kind of wonder what the command latency, if latency has anything to do with the I, because it's very reactive. What if we change the I to a lot less, ki to 0. What if we disable the I term completely? Just starts to run away. What happens if I add more I term? Like 0.05, 0.03 instead of 0.025. What about 0.04? set the D term more. So if we bring this back to 0.25, D as 1.2. Lots of oscillation. Interesting. Okay. So I got this jitter of like 0.5 degrees in either direction. I wonder if there is any... I really wonder what's causing it. You know, it could be the backlash. I also wonder if there's any sort of like algorithms out there to fight the oscillation buildup. Model predictive control type stuff. I mean, other than that, like, I mean, it is balancing. It just doesn't go anywhere. All right, let's see. What time is it? It is 10:08. Okay. All right, I think we can probably start copying in the encoder logic now. We have a rudimentary ability to configure this thing. We need to add it to the visualization tool at some point, but we do have this command line utility that can update it. All right, so let me turn off the motors. And let's plug this back in. All right. So we now have a visualization tool, and we have a what do you call it? A way to set the constants over the network. So let's see. This whole thing is now starting to get kind of long. It's 400 something lines long. Okay. I think the next step is to copy in the PID, not PID, sorry, the quadrature encoder control stuff from the Pico samples. So we're going to delete all this argparse stuff. And now we're going to, oh wait, stop doesn't actually do anything. So, let me just delete that. Delete this cell. All right, see what happens if I restart the notebook. Click run all, essentially. Should give me my thing, right? Main is not defined. What do you mean main's not defined? Run all cells. There we go. 1000. There we go. All right, that's cool. All right. Okay, so now let's. Wow. Yeah. Let's commit this code. Git add tools. -m add beginning add visualization tools. Visualization tools and remote and PID and setting PID constants over the network. And setting PID constants over the network. Okay, we'll add that. We will remove the pi cache because that's stupid. Oh, Jesus. Right. Don't want to commit. Git add dot git status. Git reset dot tools. IPy. Let's get reset tools. Balancer. Pi cache. Vim dot git ignore. IPy and B checkpoints, iCache. Git id. Alright, git commit -m. Git push. Alrighty. Now y'all can have this stuff too. Perfect. Let me just see what the GitHub looks like. Pico balancer. Tools. What if I do this? What does this look like? Putting a bokeh. Okay, more or less the way I left it. Perfect. Okay. Nice. Nice. All right. RTOS task notifications. Pico examples. Alrighty. We are going to go to the PIO samples. And we are going to go to the sub-step quadrature encoder. Or, well, do we want to, do I have the time to figure out sub-step right now? Alright, actually, yes. We shall use substep quadrature encoder.pio. We're going to grab the raw version. Okay. We're going to add under sources, new file. We're going to do quadrature encoder substep.pio. Install that in. It's all nice and good. Alright, we're gonna go over here. We're gonna take some of this stuff. We're now going to need to set this work. Pin A. Where is that? Where's pin A? Knit PWM. Substep state. Read PIO data. Will this work in an RTOS is a good question. Fig is a function. Substep update, get step start transition. Okay, this might be a little much for now, so let's just go back to the simple quadrature encoder decoder. So we'll just go to the raw version of this. We'll migrate to the substep version at some point. New file, quadrature encoder.pio. Paste this here. Alright, remove that. We'll go here. Actually, yeah, yes, go there. We will do include Pico. Actually, sorry, hardware pio.h. Perfect, and we're going to include quadrature encoder.pio.h. Now we're going to go to the CMake list. We're going to go to here. Going to say hardware PIO. And then a PIO generate header. And then we're going to add is that it? I think so. All right, perfect. Nope, nope. PIO. Okay. Perfect. Perfect. Nice. All right. So now if we go back to the C program, we can base pin must connect phase A of the encoder. Okay, which did I attach my encoders to? Those come from, it looks like 12, 13, 14, 15. Okay. 12, 13, 14, 15. And I don't know which is which. Okay, well, either way. We're going to set up the PIOSM. Okay. Okay. What all pins are defined up here? Okay, sorry. Define motor left phase A, motor left encoder A is 12. Motor left encoder B is 13. Motor right encoder A is 14, and define motor right encoder B is 15. All right. We're gonna go down here, set up encoders. Set up encoders. We're going to do GPIO init. Motor left encoder A as I wonder. Yeah, order A. Oh yeah, init GPIO set input enabled. Motor left encoder A. A funny one is that this should set up all of it. Actually, we don't have to do this. So we do PIO add program. We're going to do PIO 0 quadrature encoder program and quadrature encoder program init PIO 0, 0, SM0 pin, it's motor left encoder A, and max step rate. What? Used to lower the clock to save power, passing zeros of the clock to maximum. Okay, I don't care. Okay, cool. Let me do that. And then, so we set up the encoders. We then, I'm actually going to add these to the, I'm gonna actually just add these to the PID response packet. Let's see. New value, old value, last value. Just, it's an int, right? And left, int, right. Well, just make it easy. Let's say left equals quadrature encoder get count PIO 0, 0. Dot right equals quadrature encoder get count 0, 1. All right, and then we got to change this in our for Python tools, balancer, PyCache, types, motion. Left C types dot C int 32. Right C types dot C int 32. All right. All right. Well, that really just that does it. Compile. Deploy. SWD. Go to here. Reboot that. We then create. I'm just going to create a P position figure title equals encoder values axis label example y axis label equals response width or actually value width equals 800, height equals 480. Yeah. Left line equals P position dot line X left source equals source PID line width equals 2, color equals red, alpha equals 0.8, and then right line handle position equals show P position note handle equals true. Right, green. All right, and then we're gonna say left equals 0, right equals equals 0. All right, left, right, might be okay. Push notebook, handle equals handle position. D left equals PID dot left right equals PID dot right. Aye, there we go, reboot. Do that, output notebook, do this thing, coder values, do that, oh wait, main. Nothing's happening, okay. Well, that's not doing what it should be doing. That's unfortunate. Others didn't come on either. Ah! Maybe we gotta reboot the CPU. Hold on. Oh, it's not happy. Not happy indeed. Why is it not happy? Ah, interesting. If the FIFO has n entries, we fetch them to drain the FIFO plus 1 entry. Guaranteed to not be stale. Uh-oh. Alright, well, we'll just do that. And we're gonna run in debug mode here. We're gonna debug this. See where we go wrong. See where we go wrong. Oh, did we even get there? Where are we? Pause. Ah, yes, perfect. Call stack. There's my call stack. Core 1. Ah, yes, get blocking. Oh, okay. So if the motor's not spinning, this gets stuck. Okay, that's not cool. Get count. Well then, we're gonna need a okay. Interesting. Okay. So let's let's add. I need to modify that. I can't have that happen. Dependencies build. Coder dot push no block. I mean, that's nice, but there we go. Get count. Static inline. Okay, we're gonna say right and FIFO has n entries. +1. This one entry is guaranteed not to be stale. If n if not n, return default while n += 1, return ret. Seems like a do while kind of thing. While and if it's 0, that's 1. Minus greater than 0. Yep. Well, and minus greater than 0. Why is ret interesting? Okay. 2. Alright, yeah, here we go. So we'll do this. We'll do this whole good thing. Alright, get count non-blocking. We do get the level. If it's empty, return our default value. Otherwise, basically do that. I mean, we could do our own thing, you know, but just to make sure. Nah, that should work. Let's see. I mean, come on. All right. Left encoder, right encoder. We're gonna say equals 0 equals 0. We're gonna say before we even compute the angle error, because left I say int 32 encoder, actually left encoder, maybe it's left encoder, maybe it's right encoder, left encoder equals quadrature get say is a left encoder. Right encoder. This is 32 underscore T. Alright, left encoder equals quadrature get count non-blocking. Yeah, 0, 0, previous left encoder. That's right encoder. I guess I compile on that. Nope. I missed something. Ah, I did, yes. Okay. Return. Yeah, there we go. Compile. Missed something. That's a messed up. That's a keyword. All right. IRQ int 32. Static inline int 32. PIO. Oh. Burp. Derp. Okay. Compile. There we go. I made some syntax errors. All right. We're going to say previous left encoder equals left encoder. Previous right encoder equals right encoder. All right. That should be good. And then, all right, compile, run, debug. All right, PID response. Alter pitch. All right, what if we turn a motor and we do not get any values? That is unfortunate. Uh-oh. We don't get any encoder values. That's not good. Okay. Well, did I do that right? Am I reading this correctly? These all plug into this. Let's go there. Those are 12, 13, 14, 15. Yeah. Yeah. Those look right. This one, set pull up. And pins, jump pins. I mean, come on. Maybe the program's broken. That program, negative, instruction memory, load negative for backwards error. Maybe if we did PIO 1, maybe PIO 0 is used by the what do you call it? The other, the SPI controller for the Wi-Fi. Stop that too. Alright, cool. Compile. And debug. Alright. Well. Nope, it's still sitting at 0. Ah, darn it. Why? Why are you 0? Why is this 0? I know the encoder's not work anymore? I mean, come on. Oh, I forgot to call the... okay. Okay. I forgot to... That's annoying. Okay, oh, dearie me. I forgot to set up the code for... I forgot to call the setup function. Oh, this is what happens when you code at 10:30, 10:40 at night. Alright, perfect. Alright, compiled, run the debugger. I'll watch this connect, and then hopefully we'll see eventually data pop up. Yes, there we go. And if I turn motor, it still doesn't work. Okay, well, let's try the... Maybe PIO1 was the way to get. Wow, I'm really having a day here. Okay. 0, 0, 0. Boop. All right. Painful. Yes. And the red line is... Yes. The encoders are now working. I can turn the wheel with my hand manually. We can see the position. And the red line was the left, but this is the right motor. So I gotta flip flop. All right, and then if we turn the wheel, forward is forward. As we go forward on the other one. Good. And turn both of them at the same time. That's the left motor, the green one that I'm turning, and it's currently set. The green line is the right line. So okay, so I just need to flip-flop my pin groups here. So this is going to be 14, 15. This is 12, 13. All right, and we'll just stop that. Pico debug. We'll come back up. Yes, there we go. Right is green, left is red. We're running. Perfect. And if we actually turn on the motors. Alrighty. It's actually... Find that little cable. And then reboot the CPU. Network's going to start sending. Alright, we're going to try to get up to 0. Alright, cool. As we approach 0, there we go. If I twist the, if I turn the robot, the number, it converges. Or look the other way. Ah, fuck. Why is the motor... see the encoders counting. Cute. Okay. Okay. Nice. Yeah, we're just turning the robot over and, you know. Alrighty. So, we've got encoders running. We've got, alright. Power down the motors here. Alright. So, we've got encoders working now. And we've got, we can power this down. All right, encoders are working. So we are going to be able to soon add, I guess position control will be the next major step. All right. So... Cool. I love it. Perfect. Alrighty. I think that is probably where we will call it for tonight. So we've got encoders working. We've got a remote network visualization of the onboard data working. And we've got an ability to set PID contents over the network. So I think that's a good place to leave. It's over 4 hours in. So I think that's a good place to leave things for tonight. And next week we'll pick up with doing a remote control of the balancer so that we'll use the encoders to basically measure the position of the robot, and we will add the ability to control it with a remote control from the desktop. So I guess check in next week for that, and I hope you all have a good week.